We are moving to the last presentation. The work is entitled Image Micropattern Analysis Using Fuzzy Numbers. The work is going to be presented by Professor Adilson Gonzaga from EESC USP. Feel free. Thank you.
Good afternoon. First of all, I'd like to apologize for my accent and reduce the vocabulary. I'm not completely fluent in English, but I will try to make me clear. I'm going to present my work, our work, image micropattern analysis using fuzzy numbers. I'm the supervisor of graduate students working with computer vision and image processing. Okay. This work try to consider pixels of the image as fuzzy numbers. When we acquire images, the acquisition process and noise is responsible for the uncertainty of the pixel value. By treating these pixel values in a neighborhood of the image as a fuzzy set, we can capture the inherent variability of these values. So, looking at this neighborhood, the central pixel of this neighborhood has a value, but we don't know the right value due to the noise, due to the image processing acquisition. Example, if you have a homogeneous region of an image, the membership, if each pixel value could be considered as a fuzzy number for a fuzzy set. So the membership degree of this central pixel must be 1 if the region is homogeneous. But if the region is not homogeneous, like an edge, this membership degree is less than 1. The question is, which is the membership function that better describes the membership degree of the pixels of the central pixel to its region? I don't know. We don't know. But we published a work in 2007 and 2009 using a triangular membership function. The triangular membership function has this equation. If the central pixel is this value, we can calculate the membership degree of the central pixel to its region using a triangular function, using a neighborhood of 3 by 3 pixels. With this work, we prove that we can extract edge using this approach. For texture analysis, for local texture analysis, Ri and Wang published a work in 1990 called the texture unit. They evaluated the neighborhood of a pixel as a micropattern, and using a weighting matrix based on a power of 3, using a function that compare the central pixel, the value of the central pixel with the pixels of the region, and if the central pixel is less, equal, or greater than the others pixels, they use a power of 3 and calculate the texture unit for a region. In 1996, Ojala, Pitcairn, and Howard published the LBP, the local binary pattern. As the texture unit, the binary pattern using a weighting matrix based on a power of 2. The micro pattern that we call this is the region under analysis, is multiplied by a power of 2 using this function, only 1 or 0 if the central pixel is greater than or equal or less than the pixel of the region. So we propose the local fuzzy pattern, LFP. Different membership functions may be based on the properties of the micropattern neighborhood. We propose that the membership degree of the central pixel, we call the GAIJ, to the micropattern defined within a neighborhood should be determined by this equation. The membership degree, the summation of the membership function multiplied by a weighting matrix and divided by the summation of the weight. The value of the membership degree of these pixels is in the interval from 0 to 1. By using the LFP equation and the triangular membership function proposed by us and the weighting matrix, this weighting matrix, we have the fuzzy number edge detector that we proposed in the past. If we use our equation, our equation, if you use our equation, the LFP equation, with the this membership function, where the sign function is -1, 0, and 1, and this weighting matrix, we have the texture unit from He and Wang. If we use our LFP equation with the step function for the membership function, and the weighting matrix this way, we have the LBP code if we multiply the membership degree by the summation of the matrix. So the LBP can be derived directly from our formulation. So we use for the LFP the sigmoid function, because the sigmoid function is a smoothed version of the stepped function used by the LBP approach. Look at that LBP approach is a crisp function, from our approach. Example, if you take a texture and a region, a neighborhood of gray levels, the membership degree is the summation of the membership function multiplied by the weighting matrix. If you calculate these values, you multiply by 255 to get 256 bins for the histogram. The same for the LBP, 256 bins. For example, this value is 114 for the central pixel of this region of the micropattern. So, taking the Brodats album and 1,110 samples, 50 by 50 pixels, we calculate the best slope for the beta from the sigmoid, the value of the beta is the slope of the sigmoid function. So, taking the beta 1.005 by training all these samples, using leaving out, and the chi-square distance, comparing all the histogram from each samples to the other samples. We calculate the beta 1.005. And using the same beta and the same function, we took the Altex TC10 test case, 24 classes from the Altex. 24 classes of texture digitized under incandescent illumination and 9 rotation angles. The Brodats album don't have rotation, texture rotated texture. And taking the training set, the 48 samples from the image at 0 degree, and the test set, the remaining 3,820 40 sample from the other 8 rotation angles. The results were, for the Brodats album, the LFP has a hit rate of 85% and LBP only 8%. It's curious to see that the better performance of the LFP, for example, for this texture, the LFP has the correct matching for all the 10 samples used, and LBP only 4 samples. For this, LFP, the correct matching 9 samples, and LBP only 3. The LFP 8, LBP 2. The LFP 7, LBP 1. And for better performance for the LBP, LFP has the correct match 8 and LBP 10, only difference of 2 samples. LFP 7, LBP 8, only 1 samples. Our approach don't has a correct match. LFP 8, LBP 9, LFP 9, LBP 10. And for the Altex TC10 database, we used the basic LBP and the 2 rotation invariant versions of the LBP. These 2 rotation invariant versions for this database only they have the hit rate of 79%, 84%, and LFP near 93% of the correct hit rate, correct matching. Of course, we waste more time for this calculation. LBP for the average time of code generation, we waste more time, 27.6 seconds to generate all the codes for this database. Okay, we are using MATLAB release 11 for this implementation. Conclusions. LFP, the proposed LFP, is a robust method for texture analysis based on image micropatterns. The LFP surpasses the LBP by 5% in terms of correct classification using Brodach's album. The LFP is rotation invariant. For the alt-text database, the hit rate for the LFP has reached 93% of correct classification. When using the image without rotation as query images. LBP and texture unity are particular cases of LFP. If we adopt crisp membership functions for the LFP formulation, we obtain LBP or texture unit approach. And for using the correct membership function, it's possible to codify the representative feature of the analysis neighborhood of the micropattern. We can change the membership function. We are trying now Gaussian functions and other functions, and we are having new results. I don't know we don't know the exact function for the membership function of the neighborhood of the regions. If you use triangular, it's better to edge detections. If you use sigmoid function, it's better for texture detections. Now we are trying to test scale variations for this approach and using Gaussian functions in another neighborhood width too. Okay, it's all. Thank you.
We have 5 to 10 minutes for questions. Anyone? Don't be shy. So I have some. You said you are you cannot still handle scales, right? Where is the main limitation for these right now? For not handling the scale, is the function that you need to work on?
Scale,
yeah.
Testing this approach
with multiple scales.
No. We are trying now using the sigmoid function for scale too, but it's not the function, the limitation.
Where is the limitation?
No, we don't know which is the better function for the scale. We are testing all functions. We are testing some functions, triangular, sigmoid, and the other function. We don't know yet.
Okay. You tested with texture classification, right?
Yes.
Are you thinking other applications that you can envision for this approach?
Yes. LBP is used for face identification, face recognition.
Yeah, I was about to suggest that.
We will try to face recognition and iris recognition the next time.
Yeah, face recognition. It's gonna be interesting because scale is not gonna be your main problem because normally you have the registration geometric transformation already, and LBP is quite reasonably good in that. And as you said, that LBP is a sub-case of LFP. It can be your case there.
Maybe LFP will be better for face identification. I hope.
Yeah. Okay. Any other? No. Let's thank the speaker again. Thank you.
Thank you.